Hello and welcome to the third of the lectures in this week 5 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last two lectures, we have seen what are fuzzy relations and why we need them. We also looked at composition of fuzzy relations and we saw there were different possibilities and interpretations on how we could compose given two fuzzy relations. In this lecture, we will look at two special binary fuzzy relations that we have introduced, that of similarity and compatibility relations. So you may recall that a fuzzy equivalence relation is called a similarity relation and fuzzy compatibility relation is also called as tolerance relation. Now, what is our interest in looking into these special binary fuzzy relations in depth? We would like to know if, based on these relations, whether we can unearth some useful information about the elements of the set X. This is going to be our quest in this lecture. Let's begin with a short recap of what fuzzy relations are, or what we have seen so far under fuzzy relation. We know a fuzzy relation is a mapping from the Cartesian product of sets with the unit interval 0, 1. And in the case it's a binary relation, we say an X is related to Y under the fuzzy relation if X, Y belongs to the support of the relation. Means R of XY should be greater than 0. Since they can also be viewed as multidimensional fuzzy sets, we could apply many of the concepts that we had on fuzzy sets. For instance, we could talk about the alpha cuts, and clearly when you look at the corresponding level set and for each one of those alphas that are from that level set, if you consider the alpha cuts, then what you are going to pick up are elements which belong to the relation to degree greater than or equal to alpha. And this essentially will give you subset of the Cartesian product of the spaces. And in the case of binary relation, what we pick are actually ordered pairs from X cross Y. And we also know that as you keep increasing the alpha, then the alpha cuts start to become smaller and smaller. And also that the fuzzy relation itself can be resolved or composed using the corresponding alpha cuts. Now, these are some concepts that will play a major role in this lecture here. We have also seen different types of binary fuzzy relations. We have generalized them from the classical binary relations, exact concepts. So we say it is a fuzzy relation is reflexive if R of XX is 1 for every X. It is symmetric if R of XY is equal to R of YX. We do not talk about transitivity. Instead, we talk about T transitivity, where T is a T-norm. And it is defined like this. In the previous lecture, we have seen how actually we have generalized this from the classical transitivity of relations. So it is given as follows, that max over Y element of X says that T of Rxy, T of Rxy, Ryz should be less than or equal to Rxz. So essentially we are saying that the connection strength between X and Z should be at least as much as the connection strength of X and Z through some Y that is there in the support of the relationship. Okay. So in this lecture, we are going to look a little deeper into two special binary fuzzy relations. The similarity relation, which is essentially the fuzzy equivalence relation, which means it is reflexive, symmetric and transitive, and also the fuzzy compatibility relation, which is only reflexive and symmetric but not transitive. Now, to study similarity relations means we need to know what usually are the properties of the classical equivalence relation. Why do we study equivalence relations? So this is something that's familiar to us all by now. A classical equivalence relation is something which is symmetric, reflexive, and transitive. Now, what is the need for an equivalence relation? Well, an equivalence relation always leads to a partition of the underlying set. How? Let us denote by the symbol x in square brackets the equivalence class of an element x. It is a set of all those elements y such that x is related to y under this equivalence relation. Now we know that if we pick up two equivalence classes, either they are disjoint or they are actually equal. Not just this, the x itself can be written as a union of these disjoint equivalence classes. That means these equivalence classes form a partition of x. Let's look at a simple relation. Let x be equal to z, and let's relate x to y if and only if 3 divides x minus y. This is something that we have seen yesterday. Clearly, it is reflexive. X is related to x because 3 divides x minus x, which is 0. If x is related to y, then this implies y is related to x. Why? Because if x is related to y, this means 3 divides x minus y, means x minus y is actually some 3 times k. Now, this also implies y minus x, y is related to x, because we can say that y minus x is equal to minus 3 times k or 3 times minus k, which implies that 3 divides y minus x. Similarly, you can extend that if x is related to y and y is related to z, then this implies x is related to z. What this does is, it is familiar to us now, the entire z, it partitions into 3 pieces. Essentially, the set the multiples of 3, then shifted copies of them. We have minus 5, minus 2, 1, 4, 7, and minus 4, minus 1, 2, 5. And you see that this is essentially the equivalence class of 2, equivalence class of, let's say, 0, and equivalence class of 1. And union of them will actually give us that. Now, this is perhaps one of the most important properties that favor having a classical equivalence relation or an equivalence relation on the set x itself. The question immediately arises, if we have a fuzzy equivalence relation, a similarity relation, do we have this luxury? Do we get such classes or partitions on x? Let's look at the similarity classes, the classes that we get from fuzzy similarity relations, in slightly deeper detail. Similarity classes themselves can be approached in 2 different ways. Recall, a relation is fuzzy equivalence relation if it has these 3 properties. You could look at similarity classes as fuzzy sets themselves. How? Let's fix an x0 element of x. Remember, we are talking about binary fuzzy relations. So fix an x0 from x and define this function r subscript x0 of y as r of x0 comma y. Clearly, then this rx0 is nothing but a fuzzy set on x itself. Now, what does it tell us? Rx0 of y tells us how similar y is to x0 with respect to r. Let's look at one particular example. Consider this relation. We have x to be 0, 1 and r of xy is given as 1 minus mod x minus 1. could also think of this as x related to 1. So now we are asking the question, is this a similarity relation on the set x which is 0, 1? Then we need to show it is reflexive. By reflexivity we mean r of xx should be equal to 1 for all x in x. In this case it is 0, 1. Note that this is true when x is equal to x, x minus x is 0, so it is 1. Now is it symmetric? Well, r of xy clearly is 1 minus mod x minus y, but this you can also write it as 1 minus mod y minus x, which is r of yx. So it is also symmetric. Now the question is this relation T-transitive? If so, with respect to which T-norm? Now this is not an easy question to answer if you are given a relation. As was told, from the matrix itself we can say whether the relation is reflexive or symmetric, but transitivity is not very obvious. Now as it happens, due to some interesting theoretical results that are available, we can show that this particular relation that we have is in fact T-transitive with respect to the Lukasiewicz T-norm. Recall what's the Lukasiewicz T-norm is. This max of 0, x plus y minus 1. For T-transitivity, what should we show? We need to show for every xyz element of x, we need to show that T of rxy, ryz is in fact less than or equal to r of xy. And in this case, we want to show for this relation R that we have here and the TLK Lukasiewicz T-norm. So let's start with this. So what is TLK of rxy, ryz? Is nothing but maximum of 0, r of xy plus r of yz minus 1. Now, what is r? Maximum of 0, r of xy is 1 minus mod x minus 1 plus 1 minus mod y minus z minus 1. So this is nothing but max of 0, you can cancel out this one and this one here. So it is 1 minus mod x minus y plus mod y minus z. Now our task is to show that this is actually less than or equal to r of x comma z, which is 1 minus mod x minus z. So this is what we need to show. Now look at this. From here, we know that either it is 0 or this. If it is 0, I will call this LHS. If LHS is 0, then we know that 0 is always less than or equal to 1 minus mod x minus z for any xz coming from 0. Why is this so? Note that r of xy, r is a function from 0, 1 square to 0, 1, so it is always greater than or equal to 0. So when the LHS is 0, then it is not a problem. But what if LHS is actually 1 minus mod x minus y plus mod y minus z? And the question is this less than or equal to 1 minus mod x minus z? Well, if this were true, this will be true if and only you can cancel this and you can write it as mod x minus z is less than or equal to mod x minus y plus mod y minus z. But this is true. We know this is true because mod x minus y is nothing but a metric on the set X, and metric satisfies triangle inequality. In this case, mod satisfies triangle inequality, which means this is true and hence this is true. And hence what we have is, for this relation, we have that for all x, y, z, element of 0, 1, we have that TLK of Rxy, Ryz is less than or equal to Rxy. That means this relation that we are looking at is in fact TLK transitive. Now, why did we go to such lengths to show that this is in fact a similarity relation? Now, think of this. Let's fix x0 to be 0.5, which belongs to 0. And look at what is R of x0 comma y. This is nothing but 1 minus 0.5 minus y. Now, how would it look like? So, this is 0, 1, this is 0.5. At 0.5 it is 1, and at 0 it will be 0.5, and at 1 again it will be 0.5. So if you draw this, this is a fuzzy set that you get when you fix x0 to be 0.5. What does it tell you? Remember, this is the value 1, this is the value 0.5. Now if you recall, in one of the earlier lectures, perhaps in the first week, when we were defining fuzzy set as a concept, and given a concept when we are coming up with mathematical expressions that could actually represent that concept using a fuzzy set, one of the examples that we had taken up was concept A tilde points close to say 0. And what did we come up with? We came up with such kind of a triangular function. Perhaps in some cases 0 we even may have had a trapezoidal kind of a fuzzy set. Now what this represents is in some sense similar. At 0.5, if you move away from 0.5 on either side, the membership, the similarity of those points, those values to 0.5 starts to dip. So you could look at this as expressing the fact how similar a point or how close a point y is to 0.5. Now instead of 0.5, if you take it to be 0.3, all we are doing is we are actually just displacing this fuzzy set. So at 0.3 it is 1, at 0 it will be 0.7, and at 1 it will be . So you see here, from this relation, if you fix one of the elements, because it is symmetric, it doesn't matter whether you fix the first component or the second component, what you get is a fuzzy set which represents how similar that point is with respect to the concept as captured by the relation. So in this case, where we are dealing with 1 minus mod x minus y, perhaps it tells you how far away a point is to that particular x0. Now this should not come as a surprise, because what we have actually is mod x minus y, which measures distance, and 1 minus of that can be looked at as how similar these 2 points are. In fact, we will see this in a little more detail in the next 2 lectures to follow. Distance and similarity are in some sense dual of each other. Well, coming back here, so we see a similarity class. That means each row or column in a fuzzy similarity relation, the matrix of the fuzzy similarity relation, can be looked at as a fuzzy set expressing how close or how similar an element is to the pivotal element of that row under the relationship R. What is the second way to look at similarity classes? We would like to see if in some sense it also can do what classical equivalence relations were able to do. That is, can we get classical partitions? Remember, we said that from given this fuzzy relation, the alpha cuts will essentially give you subset of the Cartesian product. So do they form? So using that, can we actually come up with partitions of the underlying space X? Recall, this is your alpha cut. What can be shown is, if your similarity relation is actually min transitive, then it is possible to come up with classical partitions for almost every alpha that you have there. That means from the corresponding alpha cuts, it is possible to come up with a partition of this set X. Let's see how this can be done with an example. For the moment, consider X to have these 7 elements A, B, C, D, E, F, G. Let's take a similarity relation. So that this is a similarity relation can be verified, but not without much difficulty, because it's a 7 cross 7 matrix. It's not easy to look at all possible combinations. Okay. So let us for the moment believe and agree that this relation is in fact min transitive, and it will be validated as we go along because of the partitions that we get. So let's take this similarity relation and let's start to look at the corresponding alpha pairs. So we know that for this similarity relation, the level set will consist of the unique alphas, which are 0.5, 0.7, 0.8 and 1. So we could have 4 such alpha cuts on this fuzzy relation, which is a similarity relation. Now if you only highlight those values which are above or greater than or equal to 0.5, so your alpha cut would look like this. I'm just highlighting the values which are greater than or equal to 0.5. So essentially we are saying that these are the elements, pairs of elements which are related to each other to at least a degree of 0.5. Now it is not apparent how we can get a partition of on X from this matrix. So now let's look at this matrix in a slightly different form. That means let's consider the corresponding alpha cut, which is written in the form of an indicator matrix. That means wherever the value is greater than or equal to 0.5, we will put a 1. So the corresponding alpha cut would look like this. It is clear from this matrix, which is actually a classical relation on X, that it is reflexive, symmetric, that it is transitive can also be seen by the block nature of this matrix. For instance, if you take this element, it is related, so this is A, this is B, A is related to B and not related to anybody else, then B is also related only to A. If you look at this, it says C is related to everybody else, C is related to D, E, F and G, and what is interesting is D, E, F and G in turn are related only to these 5 elements and nobody else. That's what we mean by an equivalence class. What do you mean by an equivalence class? X is related to Y means X is related to every element that Y is related to. In turn, Y is also related to every element that X is related to. So clearly you see a block matrix kind of a structure here, and this allows us to write the following. So we can obtain a partition of X at the level of alpha equal to 0.5. What would this be? So look at this block structure. It means we have X is AB. So these 2 elements are related to each other to a degree greater than or equal to 0.5. And all of these elements, C, D, E, F, G, they are related to each other. Any pair of elements that you take from here will be related to the degree at least 0.5. Now, X consists of only these 7 elements, and we already have a partition at this resolution. Now look at this. This is a partition that you have got on X when you do not, when all you insist is that the similarity between any 2 elements within the class should at least be 0.5. You do not care whether it is above 0.5, 0.7, 0.8. You only care that it is greater than or equal to 0.5. You don't insist on anything more. And you actually cut off anybody who is not related to another person, another element, to a degree less than 0.5. Of course, this is the smallest alpha here in the level set. So we would have almost everybody here. But now what happens if you increase it and move over to the next alpha? let's look at 0.7. That means all of these are not going to come into picture. And if you draw the corresponding matrix of the alpha cut, this is what you see. All of these are 0. However, this 1 will remain because it is reflexive. Now once again you see, because of transitivity, we get a nice block matrix kind of structure, and for this, at this resolution of alpha, the partition that we get is AB union CD, EF and G. Now nicely, it is in fact a resolution of an earlier partition. That means this is one partition. Now we are actually making it much more granular, finely granular. So at 0.7, this is how the partition of X could be. That means if you insist that in the classes, any two elements should be related to at least the degree 0.7, then these are the ones that are sticking together. G separates out. A and B are still sticking together. Now let's up the ante and go to the next alpha level, resolution level. So all of these elements do not play a role, and accordingly that is seen here. You see the corresponding indicator matrix, this is what you get. And now you see here that the partition is further refined. Now F also separates out from the previous set. F is not related to at least one or more of them in this set to a degree greater than equal to 0.8, and so it separates out. But A and B still stick together because they are related to each other at least to a degree 0.8. Now if you go to 1, then these are the elements that will remain, and the corresponding indicator matrix is this. And from here you see that even A and B start to separate, but C and D, they actually stay together. That means C and D, they are related to each other under this relationship to a degree 1. In essence, they are saying that there is not much difference between C and D. Well, so given a fuzzy equivalence relation, a similarity relation, we may not be able to get a single partition, but at every resolution, we are able to partition the set X. And when you threshold it, so essentially what we are doing is we are thresholding a particular alpha, and because of transitivity, min transitivity of the similarity relation, what we can ensure is this: the matrix that we get, the relation, the classical relation that you get after thresholding is in fact transitive, and it leads to equivalence classes or a partition of the set X. Now let's look at fuzzy compatibility relations, which are only symmetric and reflexive. They are not transitive. Can we obtain a similar concept of compatibility classes here? Yes, we can. For instance, once again, if you fix an element x0, you see that it essentially gives you a fuzzy set on X, and you could still say that it measures the similarity between any element Y and x0 under the relationship R. This is clear because it's only a fuzzy set. We don't have any further restrictions. The question is, what about partitions from the corresponding alpha cuts? Do we obtain classical partitions from alpha cuts? Well, sadly no. We will see why with an example. Once again, we consider the set X to be a set of these 7 elements A, B, C, D, E, F, G, and consider this relation S, which is a compatibility relation. Clearly, it is reflexive and also symmetric. But the question is it min transitive? Well, to prove transitivity is difficult. To prove it is not transitive, perhaps it's easier because we need to produce just one triple where the transitivity does not hold. Luckily enough, we are able to find such a triple here. Look at these values. So you have A, B, C, D, E, F, G here and A, B, C, D, E, F, G here. And look at these three numbers. So 0.5 is actually S of GE, 0.4 is S of GF, and 0.7 is S of EF. Now if you look at minimum of S of GE, S of EF is equal to minimum of 0.5, 0.7. Clearly this is not less than or equal to 0.4, which is actually S of GF. Recall, what we want is for transitivity, for T transitivity, we want that T of r of xy comma r of yz should be less than or equal to r of xz. That means r of xz should be at least as big as t of rxy comma ryz. In fact, for every y, that's what we want. We also put a max here. But even for one y, if this is not valid, then we know that it is not transitive. In this case, we are looking at min transitivity, which means this t is min. And what we have shown is there exists at least one triple for which this inequality is not held, which means this is not min transitive. Okay, so now, as was stated earlier, you could look at the first row and third row and say, okay, this is giving me a fuzzy set which tells me how much similar other elements of the set X are to me, which is C. So if you take the last row, it tells you how similar other elements of the set of X are to the element G. That remains. The approach 1 is valid here. But the question now is, from the alpha cards, can we get partitions of the set X? And we have shown now this is only a compatibility relation. At least it is not min transitive. Now, once again, let's look at the alpha cards. Now there are 5 distinct alphas here, 0.4, 0.5, 0.7, 0.8 and 1. So let's look at the indicator matrix for the value of alpha being equal to 0.4. Now this is what we get here. Now, this does not seem to have a very clear block matrix kind of a structure. Of course, you see here, A, B, they are related to each other to degree 0.4 and nobody else. So in that sense, they appear like an equivalence class. Because remember, equivalence class means that if X is related to Y, then X should be related to every element that Y is related to, and in turn, Y should be related to every element that X is related to. It appears that that happens with these two elements A, B. However, if you look closely, we also have this kind of a block. Now, what does this say? How are we highlighting some blocks among this submatrix? All of these elements, C, D and E, they are related to each other to a degree of at least 0.4. Now, remember, if D is related to E and E is related to F, then we want that F also should be related to C. So C is related to D, D is related to E, then we want that C is also related to E. Now, all of them have, from this set, any pair of elements that you take, they will all be related to each other at least to the degree of 0.4. So that means this again forms a similarity class or a compatibility class in this case. Now we also have other kinds of blocks. Look at this. All of these elements share the same relationship amongst themselves. That means if you consider D, E, F, G, any pair of elements in this D, E, F, G will be related to each other at least to degree 0.4. Thus, we have these 3 compatibility classes. Clearly, these compatibility classes, they form a cover of X. That means their union is X. However, they are not necessarily disjoint and hence they do not form a partition. They only form a cover. Now, allow me to record them differently because when you go one level up, it shows something else also. So what we have is, we have this set X with 7 elements. Now, if alpha is equal to 0 or any value less than 0.4, all of them will form the compatibility class. However, at alpha is equal to 0.4, what we see is these are resolving like this. We have AB branching out. We have CDE forming another compatibility class, and we have also DEFG, which forms a compatibility class at the resolution level alpha is equal to 0.4. Now let's move one step further. Let's take alpha is equal to 0.5, which means these two elements do not come into picture and the corresponding indicator matrix looks like this. Now, are there some blocks that we can find here? That means self-contained set of elements which are related to each other, and every element is related to everybody else within the set up to a degree 0.5. Once again, we have these two. These three also remain, that is C, D, E. Now, you see that D, E, F, G, we have only D, E and F here, but interestingly, we also have D, E and G. So that means what has happened is A, B, they have continued to remain together. C, D, E also have continued to remain together. Now, interestingly, from D, E, F, G, D, E, F have split like this, and we also have another compatibility class which is D, E and G. So while increasing the alpha cuts, or resolution level alpha, we have more compatibility classes. We see that they are not disjoint, they are overlapping. Now, this is happening because this relation is only reflexive and symmetric, but not transitive. So transitivity, min transitivity is very essential if you want to actually have a partition on X. Now the question will arise, so what? What if we have only compatibility classes which anyway form a cover of X? Well, the question is, how much information are you able to gain from these compatibility classes? Typically, it is well known that if you have partitions, then you are essentially able to group the elements of X. Now with these overlapping sets of compatibility classes, if you are able to intelligently interpret them, yes, fine, but otherwise we are at a loss on how to unearth some information from these compatibility classes. So typically what we want is transitivity. Now let's also look at a particular practical application. These days it is common to talk about social network analysis, wherein you have lots of nodes representing perhaps people or objects which are related to each other, and what you have is essentially a graph, perhaps a weighted graph. The moment you have weights, you could always normalize them and bring them down to say between 0 and 1, the unit interval. So essentially what you have is a weighted graph whose adjacency matrix looks like a fuzzy relation. Now, if you have only this, we know that typically these relations are symmetric. That means if X is related to Y, to some extent Y is related to X to the same extent. For instance, this graph, if you take two of these nodes, they could indicate on a given set of attributes what is their preference, to what extent they agree or disagree on the preference. So that this graph could actually represent that. And if you have another graph like this, for the same set of people or a different set of objects that you are considering, it could represent some other preference relation. Now, how do we make sense of these objects from these relationships? Remember, these relationships may only be symmetric, and we could also put a self loop here and then assume that it is reflexive. So essentially, you might only have a compatibility relation, not a similarity relation. So now if you want to obtain some information among them from this, one of the first things that you would do is to actually group these objects, which is essentially clustering them. And since you are going to do clustering based on the relations, then it falls under the large class of clustering algorithms called the relational clustering. But remember, if you want to look at it from the lens of fuzzy relations, then what you would perhaps want is actually a fuzzy equivalence relation, a similarity relation. However, often these are data that are given to you. We do not have a nice mathematical form which generated this, and often they end up being only compatibility relations. That means they are only reflexive, or they could be made reflexive. They are symmetric typically, but they may not have transitivity. And even if they have transitivity, perhaps, but as I said, you may not be able to find out what is that transitivity, and it may not be meant transitive. So the question is, how do we infuse transitivity into fuzzy relation? So the need for transitivity is clear. If you have a compatibility relation, by infusing transitivity, you make it a similarity relation. And once you have a similarity relation, you are able to partition this underlying space X. And you know that it is beneficial in many applications. In fact, in the next lecture, we will touch upon this, how hierarchical clustering can be looked at as relational clustering using fuzzy equivalence relations or similarity relations. Hence, transitivity plays a vital role when you want to do some basic data analysis given a set X of objects. So in the next lecture, we will discuss how to infuse transitivity into given fuzzy relation. A good source for the topics that we have seen in this lecture is the book of Clare and Yuan. Almost whatever we have spoken about on the compatibility and similarity classes are available in this book. Glad that you could join us for this lecture, and hope to see you in the next lecture soon. Thank you.